Hi guys, and welcome to today's video on exponential growth and decay, part of the Mathematical Methods Units 3 and 4 course here in Australia. If you are new to my channel, don't worry about it if you are not in Australia. This stuff applies universally. I'm just tying it into a bit of a course that I am teaching over here, but please do continue watching. If you are new, can you do me a favor? And in that corner over there is a arrow pointing to doohickey, which asks you to subscribe. I have no idea whether these videos are useful, but by you subscribing, it shows me you're watching and that I'm not sitting in a room talking to myself, going ever so slightly crazy. So great if you can subscribe and invite a couple of your friends to do so as well. Much respect. Now, exponential growth and decay. This is actually the last lesson in a series of videos on exponentials. We've looked at how to, basically solve them and manipulate them, move them around, all that type of stuff. And it is incredibly important to be able to do that. Why? Well, when we are trying to find powers, then it is important to have tools that if the power is unknown, say an x or a t or an m, that we can bring that down in a sensible way. There's not always a situation where we can use our CAS calculator. So that's very much what we have been dealing with. As you can see above me now, we can see that there is a learning for you to be able to do in terms of cell growth, radioactive decay, and population growth, and using that and extracting information from questions and solving them using all the rules for exponentials and logs that you currently have. Okie dokie. Well, there are three main cases that I want to look at in this particular video, and one of them is cell growth. Now, hopefully none of you who are still at school have had a baby, and that would a little bit scare me. But anyway, cell growth. If you know anything about babies, then you know that a little fishy thing swims to a little eggy thing, and then they sort of do all sorts of exciting stuff, and then cells are created. And over a period of time, every day I think it is, the cells start to subdivide. So we had one cell that goes to 2, 2 cells go to 4, 4 cells go to 8, 8, 16, 16, 32, and so it goes on. Now, if we were to actually sketch that on a graph, what we would end up with is exponential growth, which would be something along those lines. It would start slowly and faster and faster and faster and faster. And so being able to look at cell growth as one case is really, really important. So there is a formula which we can use here that says n equals n0 times 2 to the power of t on td. Now, with any formula, obviously it's important to know what it stands for. So in this situation, if we were looking specifically at cell growth, be it bacterial or babies or whatever else, n would be the number of cells at a particular time. T would be the number of minutes, and it's so important there that it's minutes that have elapsed since the start of that experiment or subdivision, and TD is the generation time in minutes. Now, what that means is how long does it take for a cell division to happen? It might be 5 minutes, it might be 24 hours. The question will give you that, but it's so important here that it's also in minutes. Now, having got that information, where on earth does this value of 2 come from? And that tricks people. Now, in this situation, or in many cases, cells double. They subdivide by double, but don't always believe that that is going to be the case. Now, if they were to triple, then in which case my formula would be n times n0 times 3 to the power of t on td. All right, if they were to times by 4 every time period or generation time, it would be 4. We can also try and trick you in terms of by giving you a percentage growth. So it might well be that they increase by 10% each time period. Now, in that situation where they're increasing by 10% each time period, what would your multiplier be? It wouldn't be 0.1. Because if you multiply by 0.1, actually what happens is the values get smaller and smaller. If you are increasing by 10%, then in that situation, your multiplier would be 1.1. So anywhere you see this number here, just make sure you know by how much the cells are growing. Are they doubling, tripling, quadrupling? Are they growing by 10%, 20%? Important to know. Then it's just trivial banging some numbers in. So I've got some examples from the Cambridge Mathematical Methods Units 3 and 4 textbook, and thank you, Cambridge, for allowing me to use them. And this is an example they use. What is the generation time? Okay, so first things first, I know I'm looking for TD. For a bacterial population that increases from 5,000 cells to 100,000 cells in 4 hours of growth. Okie dokie. So bearing in mind, they're now giving me information. I've got n is equal to n0 times 2 to the power of t on td. Now, they haven't told me it's doubled, but I'm going to assume it is, right? In this situation, they wouldn't give me enough information otherwise. So we now know that n is 100,000 cells, right? So they've given me a point in time and how many cells they are. They told me how many cells we started with, which is 5,000. That's what this n0 stands for. Times 2, the power of t. So we've looked 4 hours of growth. Now, sadly, so many people will put a 4 there, but it's not. It's got to be in minutes. So I've got 4 times 60, which is 240. So that's 240 divided by generation time. Well, that's what I'm trying to find. I'm trying to find my value of TD. All right, so dividing both sides by 5,000 gives me 20 is equal to 240 on TD. I'm going to take logs of both sides to get rid of that 2, right? So anything that's to the power will then come down. So I get, sorry about moving my screen there. Let's try that one again. Let's bring it down. We get log 2 of 20 is equal to 240 on TD. And then it's just the case when I've got a fraction equals a fraction of swapping those two to say that TD will become equal to 240 divided by log 2 of 20. Now in that situation, I'd need to use my calculator. So let's fire up my calculator and take it back to main. Thank you very much. Let's go to main. And what do we want? We want a fraction of, whoops, nope, what am I doing here? A fraction of 240 divided by the log base 2, using that key there of 20, hit exit or enter, and 5.53. Now they haven't given me a degree of accuracy here. So if it was an exam, I would actually leave it as 240 over log 2 of 20. But generally speaking, with maths, we do round to 2 decimal places. So let's just say that that would be 55.53. And my units are in minutes. All right, so using that formula, taking the stuff out of the question, fairly trivial. Now we get radioactive decay. Now, radioactivity is obviously a science subject, but it's something you need to know about. And what is radioactive decay? Well, basically, we deal with things called half-lives in radioactivity. And so what that means is if you've got a block of material, which is 1 kilogram, and it's got a half-life of 1,000 years, it will take 1,000 years for half of that block to disappear. So after 1,000 years, we would effectively then have a half a kilogram. Now, sadly, a lot of people then turn and go, oh, well, okay, then it's a half, another 1,000 years and it's gone. No, the reason it's called a half-life is what it means is it's going to then take another 1,000 years for a half of the half to go. So after 1,000 years, so that's another 1,000 years, we'll actually end up with 1/4 of a kilogram, a half of a half. And then after another 1,000 years, we'll end up with 1/8 of a kilogram. And it will literally continue doing that until it will almost, you would assume, split the atom. Now, if we were again going to draw that type of graph, we would have exponential decay. It will decay really quickly to start with and slow down and down and down. How is this described in terms of a formula? Well, it just so happens we have one here. So A is the amount of material left. A0 is how much we start with. And then we have this e to the minus kt. Now, k is a constant of decay, and k is always a positive value. It is this negative here that you need to take account of, because that's the bit that creates my decay. If I didn't have that negative there, then interestingly, it would give me growth, and we'll come back to that in just a moment. So knowing that, and t stands for my time taken since the start, let's see whether we can apply this to an example. Right, the following example has been taken again. So after 1,000 years, a sample of radium-226 has decayed to 64.7% of its original mass. Find the half-life. All right, so the half-life is when my amount I have is half of what I started with. Now, bearing in mind my formula is A is equal to A0 e to the minus kt. What I'm then saying is to find the half-life, I'm looking for the point where a half, A0, is equal to A0 times e to the minus kt. Now, getting rid of that for the moment, these obviously cancel, and so I have a half is e to the minus kt. Now, we have an issue here because the question says find the half-life. That's actually saying find this value of t. How long is it before half of my material goes? Well, I've got two unknowns in that equation, which means actually I've got to find the value of k first before I can do it. So this is actually a multi-part question. I've got to do two parts. So let's go back. They've told me that after 1,000 years, all right, so I now know that t is 1,000. I've got 64.7% of its original mass. Well, bearing in mind the original mass is given by A, 0, then we know at that point we would have 0.647 times A0. And do you see what I do? It's such a simple trick, but it actually makes life a little bit easier for me. So what do I get here? So I can replace A with 0.647 A0 is equal to A0 times e to the minus k, but in this situation we know that t is 1,000 years. Yes? Now that's not the half-life in that situation, okay? That's not the half-life. That's just, this has taken 64.7, sorry, it's taken 1,000 years to get rid of, or to have 64.7% left. All right, A0s cancel. So I get 0.647 is equal to e to the minus 1,000k. How on earth am I going to find that? Well, I'm going to fire up my CAS calculator. I thank you very much. And I'm going to use the solve function. So solve, if you would, 0.647 is equal to e to the power of minus 1,000. I'm not going to use k, I'm just going to use x. And if you would be so kind to solve that for x, oh trusty calculator, gives me a value of k of 4.354089 to the minus 4. Hopefully you are all conversant with the idea of standard form, yes, or standard index notation. So that is telling me the value of k is equal to 0.0004354089845, and it continues to infinity and beyond. So knowing that's my value of k, I could turn around and say, well, therefore k is approximately equal to 0.000435 and just ignore the rest of it. You can write that down, but my advice to you is don't use your rounded value in any question. Your calculator is clever enough to be able to remember that. And for this particular calculator, you can highlight it, drag it down, and it'll remember that value for you. So having found the value of k, I can now return to that second half of my question and say, well, okay, I've got half now is equal to e to the minus kt. I know what k is. So a half is equal to e to the minus 0.000435 ... times t, and so solve for my value of t. Right, I can do that. I thank you very much. So my value of t is going to be, let's fire up my calculator one more time. So what have I got? I want it to solve, please, where 0.5 is equal to e to the power of minus, drag this down, so I'm just going to highlight it. He says I'm just going to highlight it and drag it down, although it doesn't want to drag into the right place. Let's try that again. So let's do e to the power of minus times by x, because that's the value we're trying to find, our half-life. And I'm going to say, can you do to the comma of x, x, and close my bracket, and it gives me a half-life of 1,591 years, 0.94. So again, in this situation, let's round it to 2 decimal places, or in fact, let's just round it to the whole number, 1,592 years would be the half-life for that sample of radium-226. Now, having dealt with decay, we can deal with the same idea for growth. And those of you who are looking behind me will see that A equals A0 e to the kt. It's exactly the same formula, but in this situation, we have a positive, where there's no negative sign in front of that kt. Well, okay, that sort of makes sense. We said that we're looking for population growth. Exactly the same way as our previous example. So, following a town, so the population of a town was 8,000 at the beginning of 2007 and 15,000 at the end, all interesting, of 2014. Assume that the growth is exponential, so the question is telling you it's exponential. Find the population at the end of 2016. Okay, so we know that we have A is equal to A0 e to the kt. So let's actually put some information in. We know that then 15,000 is equal to my initial value, which was 8,000, times e to the power of k. We don't know what it is, but we're going to need to find that one out, times the value of t. So 2007, 2008, 2009, 2010, 11, 12, 13 and 14. So that is a value of 8. Now that's really important to notice the distinction between the start of 2007 and the end of 2014 is 8 years. 7, 8, 9, 10, 11, 12, 13 and 14. Right, once again, I now want to find my value of k, so I'm going to fire up my trusty calculator. And I'm going to say, do me a favor, calculator, can you solve 15, 1, 2, 3 is equal to 8, 1, 2, 3 times by e to the power of 8x. And we want you to do that, please, for x, and close my bracket. Gives me a value of k in this situation of 0. So my value of k in this example was 0.0785760, and so it goes on. And once again, don't round this. You don't need to. Your calculator will work this all out for you. Right, so using that, still haven't found the population. Find the population at the end of 2016. So going to that first dot point there, we now know that we've got A, which is my population, is equal to 8,000 times E to the value of 0.07857, and I put it in brackets, multiplied by, right, 2016. So 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 to the power of 10. Fire up my calculator if you would, please. Thank you very much. For now, we'll just do 8,000 times by e to the power of, I'm going to open a set of brackets so that I can drag in my multiplier here. Doesn't really want to put it in the right place when I do this, does it? So let's try that one again. There you go, just being difficult, times by 10. Close my brackets and press enter, and it gives me 17,552.6. So I'm going to say 1,750. I'm going to say 2 people. Now the reason I'm going to say that is because actually we have got 0.6 of a person. Does it make sense to round that up? No, let's just assume they're growing some there. So if I was to physically count heads, I'd have 17,552. So that's the first dot point. In what year will the population be double that of 2014? Right, wow. In what year will that be? Double of 2014. Well, I can double 15,000 to give me 30,000. Now it is equal to, what is it, 8,000. That was my start value, times E times K to the 0.07857 ... multiplied by what year? Well, we're trying to find the value of t. So again, once I've actually extracted the information, I just put it into my calculator and get it to do all the hard work for me. Solve. It says 30, 1, 2, 3 is equal to 8, 1, 2, 3 times, where is my e to the value? Let's open some brackets. Let's try copying that x value again. And this time we'll put it right by that bracket so that it works. Times by x, because we want it to find the value of x, and I'm going to put a comma in x and close some brackets, and it's going to tell me that 16.82 years. So in what year will the population be double that of 2014? Well, if we now say that x then is equal to 16.82 years, so what we'll have to say then is 17 years. So 17 years after 2007. So 2007, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, and 23. So using that information, I would say 2023. The last part of this video looks at what I think is a harder example, but again, it's just about extracting that information from the question. Okay, so here we go. There are approximately 10 times as many red kangaroos as grey kangaroos, and I promise you, if anyone's going to make a mistake, it's going to be here in this particular question and in this particular part, right? There are 10 times as many red kangaroos as grey kangaroos. So we now know that the red kangaroos are equal to 10 times the grey kangaroos. Take a grey kangaroo and times it by 10, and you've got 10 times as many, right? So many people get that the wrong way. If the population of grey kangaroos increases at a rate of 11% and the red kangaroos decrease by 5%, how many years must elapse before the proportions are reversed? So this is my start. They now want to say, well, the end is going to be where we have G is equal to 10R. So this is what I'm aiming to. Now that value of G is basically a value of, grey kangaroos in the future. So the first thing we need to do is say, well, can I come up with a formula for kangaroos in the future on a particular time? And yes, I can, because I know that the number of grey kangaroos is going to be given by G0 multiplied by some sort of multiplier to the power of n, where n is years. Now, how do I know this? Well, it was this 11% here, because it's growing 11% per annum. It's basically like compound interest. So how do I turn 11% into a multiplier? That becomes 1.11. So that's the number of grey kangaroos. What about the number of red kangaroos? Well, I suppose it would make sense then that R would be equal to R0 times some sort of multiplier to the power of n. Now we can use the same letter of n because we're dealing with the same number of years. But in this situation, it says it's decreasing by 5%. What is my multiplier? Well, 0.95. Okay, so we know that a time in, the number of grey kangaroos and red kangaroos in some point in time is given by that. But we know that later on we're looking for at what point will the number of grey kangaroos equal 10 times the red kangaroos. So I'm now going to say, well, I know that G and G here are the same. So I have G0 is 1.11 to the power of n is equal to 10 times R, which must be the value of R, which is R0 times 0.5n to the power of n. Now, we have a small problem here because I've got way too many unknowns. But is there a way of me referencing the number of red kangaroos and grey kangaroos at the very start of this? I should Coco, that's exactly what you wrote here. That's exactly the same as R0 and G0. That's our start number. So if I now know I can place R0 with 10 times G0, so that now becomes G0 is 1.11 to the power of n. 10 times R0, which is now 10 times 10 times G0 times 0.95 to the power of n. Scrolling up to give myself a little bit of room. Well, the G0s now cancel. I thank you very much. And so I have 1.11 to the power of n is 100 times 0.95 to the power of n. And how am I going to solve that? I'm not going to do it by pencil and paper. I am once again going to fire up my CAS calculator. And I'm going to say, CAS calculator, do me the favour, solve, please. And I'm going to put loads of stuff in brackets. 1.11 to the power of, let's call it x, is equal to 100 times brackets 0.95, close brackets to the power of x. Yes, and I'm going to put a comma and an x, and I'm going to close my brackets, and I'm going to go poof. Outcomes, it says, thinking about it, 29.586. So, going back to what the question actually asked, I'm too old to actually try and remember. It says to me, how many years must elapse before the proportions are reversed? Well, in which case, we know that they'll be identical after 29 years. Now again, accuracy, would we say 30 years? Probably you would say 30 years because when on Earth is 29.59 years. But the general idea is looking in the question, extracting the information. And I get it, guys. I promise you I do. It's challenging. I know that, but it's practice makes perfect. Okay, ladies and gentlemen, we have completed exponential growth and decay. Thank you so much for taking the time watching this video. If you haven't already done so, please do me the honor of subscribing by clicking that doohickey over there. A video is loading below it, also from the mathematical methods scheme. Hopefully you're finding these useful. If you are, send a shout out to your mates. Otherwise, I'll be back with more videos. You have a good day. I look forward to seeing you soon. MaffsGuru, signing off.